All right, so now what we're going to look at is segments of a circle, or we're going to still looking at segments, but we're just going to look at what happens when they're outside of a circle. Okay? When they're outside of a circle. So in order to do this, right, what I'm actually going to do this time is I'm going to do a very similar trick. Okay? Actually going to create this triangle and this triangle. Okay? So again, we are not assuming that these segments are congruent. We're not assuming anything like that. So what we're looking at is we have two chords which intersect outside of a circle, and we're going to look at what happens with the segments, right? Because before they cut off proportionally. Let's see if the same kind of idea happens. Okay? So, the reason that I made those two triangles is because when I look at this angle right here, it intercepts this arc. And when I look at this angle right here, it also intercepts that same arc. So I know that those two angles are congruent. Likewise, both triangles share angle A, so I know that by angle, I know triangle ACD is similar to triangle ABE. Okay. Any questions so far? And once again, I'm going to look at, okay, what about, because I have similar triangles, let's look at what happens to, their side lengths as far as proportionality is concerned. Okay. So the segment I'm going to look at is I'm actually going to look at AC compared to AB. Okay. So I know that AC over AB is going to equal the ratio between, and then instead of doing instead of doing CD, because CD was the segment that we just randomly drew in here, right? So we don't want to use that. We want to look at what happens with the other pieces. Well, the only other piece we have is, AD, and we have AE. And those are actually the pieces that were given to us, okay? Again, we drew in CD and BE, okay? So, and we're trying to do this without even using these parts. So now we've got that proportion. So now we want to multiply, or now we want to use the cross product property, and we're going to see, right, that this is saying then that AE times, sorry, I wrote AE, it should be AC. AC times AE is going to equal AB times AD. Okay. And you're probably looking at that going, oh, it's just like before where it's the little part times the bigger part, little part times. Pay attention, right? Each of these segments have A in it. So what we're actually doing when we have an intersection outside of the circle is I have AB times AD. So I have the little section outside times the whole thing. And that's going to equal the little section outside times the entire thing. Okay? So that's what we have to be careful about. Okay? Now, we're going to look at the tangent segments, secant segments theorem, because this is going to be essentially the same thing. So again, when they have two segments intersect outside, okay, then we can have, if we have two segments that intersect outside, right, then we can have two secants, or we can have a tangent and a secant, and then we'll talk a little bit after about what happens when we have two tangents. Okay, so without really kind of going through all the hustle and bustle, essentially this is the exact same theorem, okay? Just the only difference is we're going to do the little piece outside, which is BC, and for tangents, the little piece outside is also the whole. So what we're going to have here is we're going to have BC times BC, and that's going to equal the little part outside. Oh gosh, that was terrible. BD times the whole, which is BE. And whenever I multiply the same number to itself, right, that's the same thing as the square, okay? So this is BC squared is going to equal BD times BE. Okay? So in essence, they're the exact same formula. The only difference is looking at this as, okay, BC's outside the circle and it's also the whole part. Okay? All right, so let's look at a couple examples. Maybe. Okay? I'm only going to do actually there's only 3, right? So I'll do them all. I'm only going to do the first 2 for time and because my text's kind of waving on me. And then I'll show you how to start essentially the third one, but I'm going to leave you guys to do that one on your own, okay? So just like before, what I'm going to do is I'm going to create points. I'm just calling them A, B, C, and this is D and E, okay? So what this theorem tells me, right, is that the outside AD times the whole, which is AE, has got to equal the outside, which is AB, times the whole, which is AC. Okay? Now this is where the tricky part happens because I have to substitute in my values. Okay? So I know that AD is 9. Okay? And then I know that AE is 11, correct? No, Curran, what is it? It's 20. Right? Because the 11 only refers to the segment or the section inside. Oh, sorry, I just wrote. Okay? So keep in mind that AE is 9 plus 11. So it's 20. And this is going to equal 10 times the whole thing, so AC, which is 10 plus X. So this is 10 plus X. 9 times 20 is 180. And then when I do this part, I have to distribute. So I have 100 plus 10x. And then from here, it's just simple algebra, okay? So I'm just going to subtract 100 from both sides. And then you get 80 is equal to 10x. Divided by 10, divided by 10. And I get x is equal to 8. Now again, I do want to check this though. Okay? I do want to check this. And so I'm looking at, okay, AD, which is, does 9 times 20 equal 10 times 10 plus 8, which is 18? Well, 9 times 20 is, what the? 9 times 20 is 180. 10 times 18 is 180. So we're good. Okay. Now we're going to do the next part. Okay. And we're going to, well, actually, I'll use different colors. We've got A, let's just call this B, call this C, and let's call this D. So now remember, in this case, B is what we call the point of tangency, okay? So, because AB is tangent, right, applying my property says that, well, we have AB, which is the outside, times AB, which is the whole, which is going to equal AC, which is the outside, times AD, which is the whole. Okay? Or another way of saying this is we're going to look at AB squared. Does it equal AC times AD? Okay? And again, we want to look at AD, which is 9 plus X. Okay? So since I know AB is 15, this is 15 squared. Does it equal 9 times 9 plus X? What's 15 squared? What? 225. 225, and remember to distribute, which is 81 plus 9x. Subtract 81, subtract 81. What's 225 minus 81? 144 is equal to 9x. Divide by 9, and I get x is equal to what? What? What is it? Baby? What? 16? Is equal to 16. Okay. Again, we want to check. And so we're going to look at, okay, does 15 squared equal 9 times 9 plus 16, which is 25? And we have 225 is equal to 225. So we are good. Any questions so far? Pretty simple, right? It will get a little bit more complicated in this case. Okay? Again, I'm going to start it off. I'm not going to solve this for you because I'm going to leave that for you guys to do. Okay? I've got A, B, C, and D. Again, since I have a tangent and a secant, I know that it's going to be AD squared is going to equal AB times AC. And when I look at AC, I know that it's x plus 5. So when I plug this in, I get AD squared, which is 6 squared, which is equal to AB, which is x, times AC, which is x plus 5. Okay? Now why this is significantly harder is I do have to distribute that x, and I'm left with 36, which is equal to x squared plus 5x. And so now I've got another quadratic. Okay? Any questions? Okay. Last little bit of information that I want to talk about is just what happens if two tangents, which can intersect outside a circle, what happens with two tangents intersect? Okay? So, if I think about this, right? Shoot. Come on, there we go. If I have two tangents intersect, okay, then I know that, right, they intersect a radii, essentially, right? And all radii in the same circle are congruent. So I know that this piece is congruent, this piece is congruent. And then if I just draw a line from the point of intersection to the center, I get that that line's congruent to itself as well. The other important thing about being tangent is not only does it intersect a radii at the point of tangency, but it's perpendicular to a radii at the point of tangency. Okay? Meaning that I've got two right triangles here, and the legs and hypotenuse are congruent, meaning that by hypotenuse leg, these two triangles are congruent. So quite simply, if I have two tangents that intersect outside the circle, right, I know that those pieces are actually congruent. And it should also make sense that obviously BC squared should equal BD squared, right? Because, applying that same theorem that we just talked about, it's still going to be true, just there's no point if they're both squared. We know they both have to have the same measure. Okay? Now, you're probably going, well, what does this do us? Well, imagine here if I have a circle, and forgive my horrid drawing, and outside of the circle I have this triangle here, which, imagine that it hits at one point here. Now all my pieces are tangent, right? Using this, I can actually find the perimeter of this triangle. Okay? Because what this theorem allows me to do is say, okay, well, if this side has a length of x, then so does this one, this little piece right here. Right? Same thing with this one here. Likewise, I can say, okay, well, if this length has a length of y, so does this one. Again, we're talking about this piece to the point of tangency, from the intersection to the point of tangency. And then if we have this length is z, so is this length. And we have each of these pieces are congruent. Okay? And it's just a little, and again, this doesn't mean it's an equilateral triangle at all. This could be some awkward looking triangle, right? But I can still find the perimeter of it, right, using this idea, just knowing that each of those pieces are equal to each other. Okay? All right. Let me go ahead and stop this recording there.